Good evening, everyone. My name is Catherine. I'm a clinical lab consultant here with WAVE, and welcome to tonight's webcast, WAVE CSP PRO and Pentacam AXL WAVE, A Blissful Marriage with Dr. Ken Mahler. You do have a text box on your go-to webinar screen where you can enter questions. Feel free to enter any questions during or immediately after the presentation, and we will have some time to go over through the questions at the end of the webcast. Again, tonight our speaker is Dr. Ken Mahler. Dr. Mahler earned his doctorate at the Illinois College of Optometry and is currently in practice in Fort Lauderdale, Florida. His practice is devoted to orthokeratology as well as providing visual rehabilitation for the irregular cornea. He's one of the foremost WAVE contact lens designers in the world, and he authored the first WAVE contact lens designer certification program. And Dr. Mahler lectures extensively on custom contact lens design, as well as providing clinical consultation services. Dr. Mahler was also one of the first doctors to start using the Pentacam corneal scleral profile scan, or the CSP software, including when it was still in beta testing. He is a fellow in the American Academy of Optometry, a fellow in the International Academy of Orthokeratology, a diplomat in the American Board of Optometry, and a fellow in the Scleral Lens Society. It's an honor to have Dr. Mahler with us here tonight, and on behalf of WAVE, thank you for your time, and thank you to everyone in attendance tonight, and you're in for a great presentation. And without further delay, welcome Dr. Mahler.
Thank you, Catherine, and welcome to all of you that have come out tonight for the this webinar on WAVE software, the CSP PRO and the Pentacam AXL WAVE system. This is webinar 10 in the series for WAVE, and let's get to all of the great information. First, my disclosures. I do consult with both Oculus and WAVE. I am a private solo practitioner in Fort Lauderdale, as Catherine mentioned. It's a contact lens only practice, and it really is devoted to everything irregular about corneas, as well as ortho-K myopia management. I do lectures and webinars like this, which is formal instruction for WAVE users, but I also do private practitioner consultation services, and there are a few different avenues for that, which I will touch on just before the end of the presentation tonight in a little more detail. I do beta test the software, both the WAVE software, the CSP, as well as the hardware for Oculus. And I am currently involved in guiding the WAVE education so you guys can get up to speed and more efficient at doing your own designing, as well as I'm involved with the further development of the software so we can do even more amazing things with WAVE and WAVE software. So let's start with understanding what the Pentacam is all about, and we really have to start with data. The Pentacam is a rotating shine fluid camera that provides us with the data off of the corneal surface and scleral surface by doing topography and tomography. We get really even further images further into the eye in the anterior segment, and can even get well into the lens behind the iris there. It is also capable of doing axial length measurements through optical biometry, as well as wavefront aberrometry. That's total aberrations that are measured for the entire ocular system. There are currently 4 models: the basic, the AXL, the HR, and the AXL Wave. And I do have a little chart at the end so you can understand which model would work best for your specific situations based on what it is that you're trying to do utilizing the Pentacam hardware within your own practice. All right, so let's start with the CSP PRO. The CSP PRO is the latest iteration of the CSP software, and there are quite a few differences between that and the basic CSP that was originally released. This is what the screen looks like, and I'm just going to go through a summary of this. First, you can see the various cross sections that are taken. On the left-hand side, you see the actual meridian that is being demonstrated through the cross section. In the middle section, where you have all of those arcs are not decorative. They're actual data that's being plotted as a result of the sagittal depths at all of those various locations. You can see that in this particular picture, there are those 25 arcs from top to the bottom. The top one is red because you can see number 1 is circled with a square circle. Pardon my geometry there, because that's the one we're actually referencing. So that's the one that's in red. And then As you look down, you can see that there are various different angles that those lines are sort of heading down south at, and that's because those are actual sagittal measurements of those cross sections, with steeper meridians approaching the lower portion of the screen faster and flatter meridians approaching it slower. If you do a cross section by clicking or left clicking on any one of those chord lengths, as well as anywhere in between, you will get the actual sagittal depth at any particular chord. We have an 18mm display here, and you can see on the CSP Pro that I have captured data all the way out to 18mm on this particular scan. There is no extrapolated data. That is full capture. The coverage map tells you how much coverage you've actually been able to obtain, and you can see that that's filled in with sort of a yellowish color, yellowish green color on the top, and a sort of a turquoise color on the bottom. That's indicating that I actually took 2 scans to get the entire display that you see there. In this particular example, what I did was hold the upper lid up and take the first scan, which is why the yellowish green color is going all the way to the top, and then just pull the lower lid down for the second scan, and that's that turquoise color that got added into the bottom. If in fact you can get the lids open all the way, you can do all that in one single take. You don't need to split that up. Up over here, you have the scleral angles being shown along with the sagittal depths at a specific chord. So in this particular instance, you can see the ring diameter is set to 16.9. And those values of 4103, 4484, and 4712, and 4842 are the actual sagittal depths at a chord of 16.9 in those principal meridians. So that's what's showing on the sort of right-hand side. On the left-hand side, those are the angles that the sclera is at those particular points. And you can see there's some dramatic differences. For example, on the inferior, you have a 47-degree angle. And then over on the nasal side, you have a 33-degree angle. So those are very, very different. And this is giving you those values directly from measurement. And then, of course, down in the lower right there, you can see a graphical and corneal representation with respect to best fit spheres. The best fit spheres are recorded up on the top. They're a little covered by the arrows there, but you can see the corneal one is 7.9 millimeters. And the best fit scleral is 11.7 millimeters, and those colors are in reference to elevations and depressions with reference to those spheres. Now, on the CSP Pro, there's actually an entire suite of scans that can be taken. In this particular capture here, the screen capture, you can see there are 4 checks on the left indicating that I took aberrometry, retroillumination, axial length, and CSP Pro has been expanded out so you can see what the actual capture screen looks like when I'm taking that on this particular left eye. That indicated that I took a full scan, which was all of those pieces of data. We do get a coverage map on a summary view there, and it does give you out to 15 millimeters what percentage of the cornea you've captured. You'll notice that on the black and white photograph behind the overlay, it looks as though the lids are in the way. That's not displaying the actual capture that was done. It's just overlaying on one of the particular images of the eye how much capture we actually caused. So don't think the coverage is saying that I caught the data off the lids on that. The Scheimpflug images are displayed to the right of that, and what's been done there is you have 2 different displays that are set 90 degrees apart. You can see on the top one there that that's showing the vertical cross section, and the bottom one is at the horizontal. And then that right arrow that I have put on there is pointing to a sort of a dot on a bar that has an up and down arrow at its extremes. And you can pull that around, and that will give you the cross sections at any one of those particular meridians, keeping those 2 images 90 degrees apart so you can get a quick view of how your actual photo capture was done with the Scheimpflug camera. And then again, on the right-hand side is the graphical, corneal, and scleral elevation maps in relation to those best fit spheres. This is an overview display screen of some of the data that we've just captured. And I've labeled the CSP Pro Plus because in addition to the CSP, which is the scleral elevation data, you can see there's quite a bit more that's being displayed here, hence my plus in parentheses. First thing you can see is that's the aberrometry data in the upper panel. And on the right-hand side, you can see the actual values of the aberrations that were captured on this particular eye. The retroillumination is basically from a backlit through the lens, so you can see if there are any lenticular opacities that are interfering with this particular patient's visual system. Again, there's the Scheimpflug images once again set 90 degrees apart, and you can pull that up and down to see them all. Axial length measurements there. On the left is the graphical, and this particular showing from 21 to 31 with the spike right where this particular patient was. And on the right, you can see that the value is at 26.458 millimeters. And then again, in the lower right, there is the corneal scleral elevation map that was in relation to those best fit spheres. And you can see those values there as well. All right, so let's get to a couple of cases and see how we put all this stuff into clinical practice. LG is a 31-year-old Black female, and she was diagnosed with keratoconus. And she had been referred to me 4 years prior to her actually coming in. The 4-year delay was due to her wonderful experience, or first experience, I should say, being put into a contact lens. Didn't go very well, and that put her off for 4 years before she came in to see me. Her spectacles are a year old, and you can see the RX there. And you could see that she's around 20/50-ish vision. The manifest refraction that I found didn't improve her vision. In fact, it was even a little bit worse. But you could see the amount of myopia is about the same. And in the right eye, I found considerably less myopia, but again, she wasn't seeing any better. She was actually seeing worse, which also underscores the difficulty in measuring optical systems for these very irregular corneas. The phoropter is not really the best device to come up with anything that has hard and fast endpoints. Health was good, no medications, no allergies, and the rest of the exam was non-contributory. And yes, she had already failed in GPs 4 years prior, hence the 4-year hiatus before coming in to see me. Here are her Pentacam scans that day, and you can see it's an obvious keratoconic set of corneas here with the sort of very elevated area fairly well centered. Down at the bottom, I also have the corneal thickness map, and you can see there she is fairly thin at 370 microns on the right and 361 on the left. This was the actual scan that I took of her eye that day. Once again, you can see the arcs of cross sections there. And you can notice that I've pointed over inferiorly to that sort of set of pink arcs at the very edge there. And you can see how quickly they're approaching the lower portion of the screen. They're really heading more straight down than, for example, the turquoise arcs that are on the left-hand side. And that's because of the inferior steepness of the inferior portion of this particular sclera. You'll also notice that the nasal side, which is where those sort of yellowish golden arcs are much, much flatter and considerably more elevated. Again, it's an 18-millimeter capture that I was able to capture there. And on this coverage map, you can see I did 3 scans. The reason for that was this was still fairly early on. And at that point, I was taking 3 scans, with the first one being central. Then I would lift the upper lid, take the superior, and then pull down the lower lid and get the inferior. Today, I pretty much take 2, or if they happen to have lids that really can open wide, I'll only take the 1. It's very, very rare that I take 3 scans now. The scleral angles are shown there along with the actual sagittal depth, and that's at a 15.8 millimeter chord. And that's for the reason that that's in fact how large this lens is going to be. So I was interested in the data at that particular chord diameter. And again, there's the graphical representation of the corneal and scleral elevation. It also gives you an average sag. So if you're not utilizing software-driven design to get to your lens, but you're actually using trial sets, you can use that average sag as a good starting point for pulling out your first lens. So that would give you an idea at a diameter of 15.8 what sagittal height you're probably going to need as an average around this eye, so that you will be able to create that central clearance of 300 microns. You can, of course, change that value. Now, this is what's called the enhanced ectasia display, and it's fantastic for identifying keratoconics. And I'm showing you this because this is a really wonderful, very quick statistical analysis that you can see in a blink how things are really looking on this particular cornea. On this left-hand side, those are a set of graphics that actually highlight keratoconus. I'm not going to go into specifics of how that's done. You can actually find an entire lecture devoted to that. But basically, it does sort of an enhanced analysis to sort of highlight if in fact you're dealing with a cone based on the elevations of both the front and the back. And you can see here, this is very, very abnormal. And we definitely have keratoconus here. In this particular area here, those are more of the numerical data that we would associate with keratoconics. You can see K values, the Kmax, which are basically self-explanatory. Talks about the pachymetry, and you can see there we're at 370, just like we saw on the first screen. Below that is the front elevation thickness, as well as the back elevation, and how that is, the thinnest point, front elevation and back elevation. And you can see how elevated they actually are, both on the front and back, 44 microns and 97 microns on the back, respectively. And then down at the bottom of that box there, you have the progression index, which is, again, another statistical analysis to allow you to understand if you're dealing with keratoconus or something that may be masquerading like keratoconus. That minimum and maximum that are in green and blue, you can see those lines on the corneal thickness graph just to the right of that. Those are the values, and what they're pointing at has to do with the progression of thinning. So the green line is where it thins the least, progressing from the center to edge, and the blue one is where it progresses the most, or the most thinning from the center to edge. And those are summarized by that artmax. And the very brief summary here is everything there in red, those are all abnormal values. You can hit the little sort of triangle that's in the lower right there to understand a little bit more about what those values mean, but I'm not going to get into that now. We talked about the corneal thickness map, and then down here is how the corneal thickness / thinness is changing from where it's the thinnest to the thickness, center to edge. The three gray lines in the upper box, those three arcs, that's normative data out to 2 standard deviation units. And you can see my patient is the red line way above that, which is indicating that this is clearly keratoconus. There's no doubt about that. And then the percentage that the thickness increases, again, those 3 gray lines represent 2 standard deviation units, with the middle being the average. And again, this particular patient is way, way below that with that red line there. So we're pretty certain we have keratoconus here. There's no doubt. Down at the bottom there, those are the numbers that we would use to describe keratoconus. And yes, everything is red because there's no doubt that we're dealing with keratoconus here. What we're looking at over there is the deviation. The first one, the DT, is the deviation of the thickness on the front surface, the deviation on the back surface. I'm sorry, not thickness, just the deviation on the front surface and the back surface. The DP, DT, and DA are referring to the thickness changes, and they're all summarized through a regression analysis to that big D that's at the very end, indicating 13.94. And that's actually the total deviation. And since you don't know what the norms are, a value of 1.6 would be suspicious, and a value of 3.0 is abnormal. So clearly a total deviation of 13.94 is very abnormal. So again, this is a very, very clear-cut case that we have keratoconus. So here are the wave lenses that I did for this particular patient, and I just want to give you a breakdown of what we're seeing here on the screen. That's the modification area where you would design up the lens. We could see the lens relationship to the cornea and sclera. The blue arc is the lens. The gray and white arc is the cornea and sclera, and those are not just pictures, they're actually being created as a model from the data that was captured by the Pentacam, with the gray being the cornea and the white being the sclera. There are the 4 control points, the red, blue, pink, and black, and you have total control over where those go, but you're basically putting those where you can get the biggest bang for your buck, so you can design the lens exactly how you want to design it. And the graphical representations, those are those 4 graphics in the upper left-hand part of the screen. We see the raw corneal data. So that's the import of the data that was collected by the Pentacam directly into Wave. So that's what Wave thinks the cornea looks like based on what we sent to it from the Pentacam data. And that's that lower left screen. And you can see it looks very similar to the graphic that we saw on the Pentacam screen. In the upper left is the fluorescein pattern. And that's a projected fluorescein pattern based on the model of the cornea and sclera matched up against a particular lens that we designed. So you can see in that particular diagram there, I have a lot of central clearance, so it's not hitting the cornea. It's landing outside the limbus, and then there's a thin ring of fluorescein indicating that I have the very edge of this lens lifted just a little bit. Down on the upper right, you can see the graphic of the lens front surface, and in the lower right, you can see the graphic of the lens back surface. And those curves are matched to the colors that are being used there on the Pentacam. So those colors are not just decorative, they're actually indicative of the colors that you would be comfortable sort of analyzing the topography itself. Up here we have essentially the textual values of the haptic data that I have. In this particular case, you can see on my upper left graphic in the quad display where it says fluorescein map, I have the radar screen pointing directly to the right, or the 000 mark. And in that direction, we can see the values for the edge angle, the deviation of the edge, and the lift angle. So that gives you the information of what's going on there. You would go ahead and grab that radar screen and drag that around for each of the semi-meridians. And of course, that data would change so you could see what the edge of the edge profile of your lens looks like all the way around. The blue that's under the darker blue line is representing the tear layer profile that's under the lens. And then in the right column there is the lens summary, where you have the symmetry of the lens, the diameter, center, and edge thicknesses, what material you used, any markings you've put on it, and of course the power values that the lens has in it. So let's move on to our patient, since I designed up that pair of lenses. This was the dispensing visit, so it was my first pair of lenses on her eyes. And bear in mind, this is done 100% empirically. I have not had any diagnostics on. So I designed up that pair of lenses based on the Pentacam data, and we see that I got 20/50 2400 vision. I clearly missed the script on this. Right eye, not too badly, but the left eye I really missed by quite a bit. But look at the potential for vision. We're down in the 20/25 range there with that over refraction. At the biomicroscope, the right and left lens were both well centered. It was about 125 microns of clearance. Flange alignment was very, very good on the right lens, showing about 15 degrees of counterclockwise rotation from my intended orientation. On the left one, there was just a little bit of excessive edge lift, both superior and inferiorly, what we refer to as toe up out at the very edge of the lens, and the rotation was about the same as the other eye, 15 degrees counterclockwise. I did not dispense the lenses because of the fact that the RX was so far off and the vision wasn't very good. She was about 20/50 in her glasses, so I let her continue with her glasses. I ordered the right lens with the power change, but I was happy with the fit, so I did not do anything about that. And then the left one, I certainly ordered with the power change because I was so far off, but I also did increase the sag at the superior and inferior edge to bring the toe down a little bit, so we used to have a slightly better profile of that particular lens. So here are my new lenses. The right one, like I said, I added the over refraction in. And then on the left one, I added the over refraction in, but increased about 120 microns of sagittal depth, both superior and inferior at the edge of this lens. Now you can also see on the front curvature graphic that the center, where it's green, now has sort of a lime green appearance up and down and a darker green side to side, indicating the cylinder that I've added onto the front surface of this particular lens design, since the cylinder has been added onto the front curvature. So my second dispensing visit, I did much, much better. In fact, the left eye was dead on target with a plano over refraction, and the right eye was off by just a little bit of minus, but I was still able to get even better than 20/25, better, improving the vision there with that little bit of extra minus. With the fit, both fit beautifully. I got about 200 microns of clearance on the right with 150 microns on the left. But what happened on the left eye is it was rotated kind of unusually at 45 degrees counterclockwise. I wasn't really expecting that. I did dispense those lenses, and I decided to hold on the changes to see how these performed, since the vision was so much better than she had with her glasses. And I did a follow-up a couple of weeks later. She said she's been wearing them full day, comfort's excellent, her vision's excellent, but she's noticing these vertical cones from a light source at nighttime. And she is improving with application and removal of the lenses. Vision was 20/40 plus and 40 plus in both eyes, and you can see they've drifted a little bit on both eyes. The right eye is pretty close to what we had on dispensing. The left eye, although it was plano before, you can see it's roughly hovering around plano. It's showing a little bit of cylinder there. The fit looked very, very good on the right, pretty much as I dispensed it. And now the left one was even stranger. because now we had a little bit of compression at the nasal pinguecula, and it was rotated about 90 degrees clockwise. So I decided to redesign and order up a new pair. On the right one, I decided to incorporate that over-refraction data. But on the left eye, I felt that the pinguecula might have been throwing the stability of the lens off a little bit, and I did want to fix that compression. She wasn't complaining, and it really wasn't red, but it was, I think it might have been hampering the fit a little bit. So these are the new lenses I designed for. I added the over-refraction to the right one. And on the left one, I added the over-refraction in, but I also increased the nasal flange clearance over that pinguecula with the hopes that it would be showing a whole lot less compression there. Third dispensing visit, now a dead on target on the right eye at 20/20 minus, no over-refraction. The left one, we're 25 plus 2. There is an over-refraction, but it really didn't improve her vision much. Fit now on the right eye, still excellent, just as it's been all along. And the left eye now is back to the proper orientation with that 15-degree counterclockwise rotation, more than likely because the pinguecula was no longer interfering with the rotation of the lens, causing the disorientation of that lens there. Lenses were dispensed. I did a follow-up 1 month later. She's doing great with the comfort. Her vision's excellent. She lost those vertical cones from the light source, and she's getting the lenses on and off very easily. She's 20/20 minus and 25 minus. We can see that there's nothing left in terms of over-refraction on the right eye. The left eye is still showing a little bit of over-refraction, but no real improvement in acuity. The fit, basically exactly as it's been all along. It looks fantastic. And so she was dispensed. Recheck her 5 months. So this case really does show that with fantastic fitting data, the first pair of lenses actually fit almost 100% of the way there. The right one, we were basically there, and the left one, other than the pinguecula and a couple little minor modifications to the edge, and then dealing with the nasal compression of the pinguecula, that just improved the fit just that little bit extra that we needed to. The only thing that I needed those follow-up lenses for really was for vision. All right, let's go to the next case. KS is a 52-year-old white female, and she's post-LASIK. She self-referred in April of 2022 out of pure frustration. She had had LASIK in 2006 and one procedure in each eye. And for 10 years, she was actually very happy with her results. But 2016, she really started noticing she wasn't seeing well. She went back to the surgeon, and with multiple visits, the surgeon did nothing. There was no treatment to improve the vision, and he basically sent her on her way. So in 2019, she found a scleral lens expert, and the doctor who was fitting these scleral lenses is a doctor that I do know fits many, many scleral lenses very successfully. So this is a scleral lens expert, and worked with this doctor for 9 months and failed due to discomfort in vision. So she wasn't able to wear the lenses and she wasn't able to see, and that was 9 months of work. Not deterred, she went to a second scleral lens expert, a doctor who I also know and does fit many scleral lenses. In 21, fit for 7 months and still failed for discomfort in vision. And on top of that, didn't have a very good experience there with the doctor. We'll leave that to bedside manner that just didn't really get along with the patient. She still can't see, so at the end, she went to, of 21, she went to a third physician. They fit her into soft torics and failed because the lens was sliding all over her eyes. So she really couldn't see very well at all. And April 22, she decided to continue, and she was able to find a way in to see me. So her glasses are about 6 months old. They were given to her for full time, but she really only wears them for close work. If we look at the RX, we could see why. Her left eye is basically getting her by for her distance activities, but being that she's 52 and already a fair amount of plus in the right eye, there's no possible way she's gonna be able to work on the computer the amount of work that she does during the day. So she puts them on for the computer and for reading. Uncorrected, she's about 20/50 minus and 20/30 plus, and like I said, that left eye is pretty much getting her by on a day-to-day basis. Manifest refraction that I found was quite a bit more plus even on that right eye with some cylinder, and the left eye a little bit more cylinder. The ed was 175, and I noticed on the right eye she has a corneal nodule at the superior nasal flap junction, which is a possible side effect. I have seen a few of these now on LASIK eyes. It's sort of like a Saltzman nodule or nodules, and they can pose various degrees of impact in terms of vision and or physiology. Health is good. She's on progesterone and estrogen. no allergies, and the rest of the exam was non-contributory. So I planned her a distance scleral lens in each eye, but we also talked about if I can get everything working well, might fit her into a multifocal, which made her very happy. So here are her scans on the Pentacam, and we can see here that's the nodule that's on the right eye. And we can see on the elevation there that it has an elevation of about 90 microns off the surface of that eye. This is what the nodule looked like on the Scheimpflug image on the top. And then on the bottom there, I just put that on there so you can get a sense of, the location as well as how high this is actually sitting off of the surface of the eye. This was the screen for aberrometry that was taken on that day. And you see I expanded out the aberrometry section, even though I did all 4 scans on the suite. But on the aberrometry, we can see over here, these results were given. And just to take a look at this, we can see why she's fairly unhappy. The vertical trefoil was the 0.612 microns. Vertical coma was 0.548. And the horizontal coma is 0.962. If we take a look over on the left there, we can see that the total aberrations due to coma are 1.21. And for those who are not familiar with normative values for aberrations, we normally expect for spherical aberration a value between negative 0.4 and plus 0.45. We can see she's at about 0.198. So she doesn't have much going on from spherical aberration, but on the coma aberrations, we expect those values to be between 0 and 0.5, and she's at 1.121, and that certainly is degrading the quality of her vision significantly. So we come over here for the CSP PRO software, and just so you can see, for those of you who delegate scans, the feedback that's given on this particular screen while the scan is being taken is information about the quality. And you can see the QS on this one is green and okay, which means that it was an acceptable quality image. We also see how much coverage we had at 15 millimeters. And in this case, it's about 84% of the eye was covered at 15 millimeters. The Scheimpflug images, once again, there are shown at the 90-degree apart, and then the graphic of the corneal scleral elevation data. This is the CSP display, and you can see this was done on a 2-shot capture, one for the yellowish golden top part, and then just for the turquoise down at the bottom when I pull down the lower lid. I set this for a 15.7 millimeter cord, and what we can see here is we can see on the graphic elevation as well as the arcs that there's an increased flatness and elevation on that nasal side. We can see that the actual other 3 quadrants are fairly equal and just really slightly depressed. So regardless of what's going on the cornea, since we're fitting the sclera, we really do need to understand these elevations and how different they are. And we can see that we're very flat and elevated sort of on the nasal, almost half of the eye, but then it really has a fairly even with the best fit sphere depression the rest of the way around the eye. You can also see the corneal nodule right there on that arc. You can see how it's bumping up that particular arc, the 4th one from the bottom. And on the left eye, this was a 2-shot capture, again at a 15.7 millimeter cord. Once again, we can see on the nasal side the increased flatness and elevation. Yet despite what we had on the right eye, we can see that we have increased superior and inferior depression on this eye. So just because we're dealing with the same patient doesn't mean that their sclera is the same from right to left, and we can't assume that. The temporal is about even, but certainly the superior and inferior portions of this contact lens are going to need to address that depression that we're seeing there. So these are the 2 lenses that I designed for this particular patient. And it's an 11.7 millimeter cornea, so I designed a 15.7 millimeter diameter lens. For distance only, that's the RX. It's a totally free-form lens, and you can see that in that graphic on the back curvature. And the sagittal depth extremes on this lens from one edge to the other, you can see it's actually just shy of a millimeter difference on the periphery of this lens. On the left eye, once again, an 11.7 millimeter cornea, so a 15.7 millimeter lens, distance only. There's the RX. Once again, it's a totally free-form design. And sagittal depth extremes on this is just a little bit less than the other, about a 3/4 of a millimeter difference all the way around this particular eye. First lenses on the eye at dispensing visit. I clearly missed the RX on the right eye by a lot of plus, but the left eye hit pretty close there, 20/20 minus, and very little over refraction got a 20/15 minus. The right lens was well centered, 150 microns of clearance. I liked the flange alignment all the way around. There was a slight toe up at the temporal edge, but there was no rotation. On the left, basically the exact same issues, along with the toe up at the temporal edge. I did not dispense these lenses given that the power was so far off on the right eye. And so on the right one, I ordered with the power chains, but I also adjusted that temporal edge to bring the toe down just a little bit. And on the left one, I was very, very happy with the fit, just that little bit of temporal edge issue. So I decided to go ahead and add a multifocal since I was already very, very close with the fit and the prescription. Second pair of lenses, you can see we've got the right eye right where it belongs now at 2015 minus, very little over refraction, and the left eye 2020 minus, very little over refraction, and she was at 2020 at near. Well centered on the right. I was happy with the clearance and the flange alignment, no rotation. Left eye, excellent, fantastic. We hit that right on target as well. So I dispensed those lenses, had her back for follow-up. She said distance vision and comfort are excellent. She has full day wear. Near vision's fairly good, but she feels strained, and she is getting better at getting the lenses on and off. Vision has remained very nice on the right eye at 2015, and on the left eye, she again is 2020 and 2020 minus and 2020 at near. So all that's very, very good. Assessing the fit, right eye is doing fantastic, and the left eye also fantastic. I decided to go ahead and order up the lens with the multifocal. The left one we continued with no changes at all since she's doing so well, and that was really to balance out just her near vision. I did get the multifocal for her. She's actually doing fantastic now with that. So here's a case that had failed with the first doctor through I don't know how many lenses over 9 months. On the second doctor through 7 months of whatever lenses they went through. And in this case, the lenses were pretty much fit on the first pair and done. Little fine tuning on the script, and that was it. All right, last case here is a 45-year-old white female. This is a little bit of a different type of a case. She's been in Ortho-K since 2007 at 30 years of age, and I was the one who put her into Ortho-K at that point. Pre-treatment RX, she was about a 4 diopter myope. She came in wearing some AccuView Oasis with HydroClear, and you could see she was seeing very nicely with those lenses. She was remarkable for allergy and regular use of oral histamines over the years from 07 through to today. I scripted out Pataday for her allergies as well as cromolyn sodium, and the rest of her exam was non-contributory. These were the original maps that I took back in 07 when she was 30 years of age. You can see on the top the curvature map, and on the bottom basically an elevation map. And these were the maps 2022, this year, it's actually just a couple of months ago, that she came in at now at 45 years of age. And we can all guess what her complaint is. She can't read through the Ortho-K that she's seeing. So we talked about getting her into a multifocal Ortho-K design. And so here are the lenses that I designed for her. 11.2 millimeter cornea. So she's in a 10.9 diameter lens. It's only set for distance only. It's still set for the treatment of -4, and they were G-SIM. And then on the left eye, you can see basically the same thing set for a 4 1/4 treatment. So what I was going to do is take the red control point, which you can see is set at 6.2. I also was going to change the central clearance there. You can see I have a little apical clearance on both of those lenses. And the power values are at plus 1.02 and plus 0.74 diopter. So I was going to modify these to all address her near point complaint. She is OS dominant, so I'm going to address that a little bit more stingily on the left eye because we want to still make certain that she has good distance vision. On the right eye, this is the process to begin the modifications. We go over to the modification area. We click on that, and this screen pops up. You can see here the optic zone diameter. So we're going to go ahead and set to the all, and the little star pattern there tells you which areas you're going to be affecting, and I'm going to affect the entire optic zone diameter. I clicked on all of that, and this comes up. We want to decrease the optical zone diameter, or the treatment area. The amount was not high enough at 0.10, so I changed that to 0.60, and we're going to apply that to the lens. We can see now that we've moved that to the red ball into 5.6. I have still that apical clearance to work on, so we're going to do that next. Let's fix the apex modifications by clicking on the modification area. This is the screen again that pops up. We go ahead to the reverse curve zone. We're going to click on that to pull the two modifications of increasing and decreasing sag. We want to go ahead and decrease the sag. So we're going to drop the apex down. Select the decrease. 1 micron is not enough, so I've changed that to 10 microns. It is an all. We go ahead and apply that. We come back to the screen, and now we can see that the apex has been dropped down. Now, the last thing I wanted to modify were the power modifications. If you remember, originally they were at, on this right eye, plus 1.02. Through the changes we made, they're now at plus 2.30. So if I left this alone, she would actually get more treatment for ortho-K, which we absolutely do not want. We don't want to reduce more myopia. We have to reduce the amount of myopia treatment that she's getting. So clicking on the modification area, we get up to the screen again, and we're going to change that base curve. Once again, we're going to modify this base curve by steepening or flattening. In this case, we are going to steepen that to reduce the amount of myopic treatment she's getting for her ortho-K. The amount at 0.25 is not enough in terms of diopters. We have to drop that from the plus 230, and I wanted to get that down somewhere around plus 0.75. So I set that to a 150 diopter steepening of the base curve. Go ahead and apply that, and here, lo and behold, we ended up at plus 0.78. So that was basically right on target for where I wanted this lens to be. We move along. On the right eye, we can see the new designs that I just walked you through. And then on the left eye, you can see I did very similar things by bringing the red ball into 5.9. Remember, that was her dominant eye, so I didn't want to reduce that by that much in terms of the treatment zone size. The apex, I did drop that down, but you can see on the power value on the left eye, we had been at plus 0.84, and now we're at 0.61. So I was very, very stingy with the amount of steepening of the base curve I did on that eye. And that basically took care of her for distance and near. This is the summary chart that I promised you on the various devices that are available in the Pentacam models. I'll leave that up there for just a second so you can take a look through that. On the left, you can see the basic, the HR, the AXL, and the AXL Wave. On the top, going across, is the CSP, that's the original. The CSP Pro, which is the one we discussed tonight. The axial length measurements and the aberrometry, and down below is which things each model is capable of providing to you. I'll just give you a second here to take a look through that so that you can see which model is the most appropriate for your types of clinical care. Okay, so in summary, the Pentacam provides excellent source topography to design software-driven lenses for corneal, scleral, and ortho-K, and in this case, obviously, we're using a Wave. The central scan provides greater chord captures than is possible with Blissful disc-based topographers. So if in fact you're doing corneal lenses, for wear or for orthokeratology, it's really nice to be able to get much further captures of corneal data that is not extrapolated out there, so that the periphery of the lens really lines up very nicely. The CSP software requires 5 captures. That's the basic software. The patient looks at a central target. It can be captured to a chord of 18 millimeters, but what I found consistently were captures of full data really between 16.5 millimeters and 17 millimeters. You really had to have a set of eyelids that you can really retract far enough to get out to 18 millimeters. On the CSP Pro software, however, you typically capture the eye out to a chord of 18 millimeters with ease. And if they can retract the lids enough, you can do it even in a single capture that takes 2 seconds. So it's very, very quick and efficient to capture the full corneal and scleral elevation data with the CSP software. It's much faster and it's much easier than it is with the basic CSP software. Most commonly, what I found, though, is I take 2 scans per eye. Typically on the first scan, I'll pull the upper lid up out of the way and take as much of the center and the upper portion as possible. And then I'll just take the lower lid and pull that down and get the lower one. Due to the way the camera system is mounted in the AXL Wave, the non-CSP Pro central capture, so I'm not capturing the scleral data, is typically capturing 90% of the cornea and some of the sclera out to 15 millimeters. So that means you have very, very good data, even with a single scan of just the center of the entire cornea and out to some of the area out past the limbus. So for things like orthokeratology, this is fantastic because you really have all the data you need just from that very simple central scan. The Pentacam directly measures the elevation data and it's not being derived from an algorithm that's being reflected off of a tear film curvature data map. And as such, tear film quality isn't an issue for the data collection, which really does help tremendously in getting good, accurate data. In addition to the topography and tomography, as well as the scleral profilometry, you also get many more metrics about the eye, such as pachymetry, densitometry, light reflectivity, transmissibility, as well as you get those sophisticated analysis displays of the corneal data so that you can really efficiently manage and diagnose various corneal conditions, certainly like keratoconus and, if you're following up cross-linking and things like that. The AXL Wave adds to the above with axial length measurements as well as aberrometry, further enhancing management of myopia progression and corneal ectasia, IOLs, as well as ortho-K treatment, etc. These are the resources available to you as a Wave doctor. So I'm just going to leave that all up there for you to take a look, but you have the clinical support, the concierge service, technical support. You also have the resources page, which has the summary of these webinars and some videos and events, as well as the email Google group where various things are discussed from peer to peer. So people will post cases and then hopefully some other docs will chime in and help out. And with that, that pretty much wraps up tonight's webinar. It was a little bit longer, but there was a lot of good information to get to you guys. So we're going to go ahead and take questions and return this over to Catherine. And Catherine, we can run a little bit over if you have quite a few questions.
Okay, perfect. Thank you so much, Dr. Mallard. That was great. I do have a few questions ready. Just a reminder, there is a text box where you can enter any questions you may have. And if you did miss part of the webinar, there will be a recording sent out as well. And so Dr. Mallard, the first question, and this is pertaining to the first case. Is there a further explanation about the changes made to address the excessive edge lift on the superior and inferior on the left lens?
There really isn't any more for me to talk about here because I just really wanted to show the approach. Getting into more of the nitty-gritty of design and the actual clicking of the various control points and all, that's a little beyond where this webinar was intended today. So basically, all I really wanted to try and show there was that based on the raw data that was collected on the Pentacam, we got very, very close, but I still will always defer to the truth, which is the eye, the lens with the eye sitting opposite me at the slit lamp. And at the slit lamp, I was able to see that we had just that little bit of excess toe up there. And quite honestly, it really wasn't bothering her. It was bothering me more than it was bothering the patient. But I saw that there and I decided, yep, we're going to go ahead and make a little adjustment to that to bring that down because long term, that's only going to help out comfort as well as stability of the lens. So getting down to very specific design changes, that would really be more of a topic of a specific webinar that we can get into possibly in the future.
Okay, great. And a second question, more general, if you didn't have profilometry, how would that have affected your fitting process at all for these patients?
Well, I can answer that non-theoretically. I did not have profilometry and I've been fitting scleral since '02. So for 16 years, I fit scleral lenses without profilometry. And the process was absolutely more arduous. You needed way more skill at the slit lamp because basically the process consisted of, I would take topographical data of the cornea, which now on retrospect, we certainly know that that doesn't indicate very much of what's going on the sclera, which I had already figured out because what I would do is take the corneal data, design up a lens, extrapolate that out to the sclera in an RSIM fashion because I wanted to keep it simple. And then at the slit lamp, take a look and see all the things wrong with the flange. Areas where it's lifting up too high, areas where it's bearing down way too low, areas where it's much, much too tight, and it's causing vascular congestion, blanching of the conjunctiva, and the like there. And then I'd go back to the wave screen and start making those changes, both in terms of location and magnitude, according to the notes that I made at the slit lamp for each of those lenses. And then refine that process moving forward through each lens design. I can also tell you from experience, I was very successful with that methodology for many, many years. However, when I got profilometry, I went back to many of those fits who were already very successful, some of them more than a decade already. And I said, I have some new technology. I'd really like to try and apply it to your lens. I went and got the scleral profilometry, redesigned up the lens, and 100% reported better performance of every single lens that I did for them. So I can tell you from experience, it's certainly possible to get a patient successful without profilometry. However, it is much faster and more efficient, and you will also ultimately achieve a much better design, both from a comfort, wearability, vision, and physiology standpoint than you're able to do from troubleshooting from the slit lamp. So at this stage where this technology is available, I couldn't even imagine going back and trying to design lenses without the profilometry. It will totally change the way you design up lenses.
That's great. And this next question is more for kind of the wave design. But when you are modifying a lens, is there an order that you recommend making the changes, kind of like an order of operations? For example, changing the optic zone before changing your sag height at the edge?
Yes, there absolutely is an order to things, because if you don't understand how the Wave software applies each of the changes, you can end up inadvertently changing some things that you really didn't want to change because you did go out of order. Again, this is a topic that's way more complex than the webinar I was preparing for you guys today. And so these are things that I may be able to hit more in a future webinar. The other thing also, I did demonstrate tonight how the modification area works, but that's actually not the only way to make these modifications. In fact, on that very last patient, patient number 3, that I showed you all those modifications, when I did the modifications, I actually did them manually. I did not use the modification area. I really did that all for this webinar so that you guys can see how easy it is to do. Because I've been utilizing Wave software for so many years, I'm very comfortable making manual changes and seeing how all of those changes are applied to the lens as I move forward. So there is an absolute order that you need to make changes so it makes good, consistent sense, and you do end up with a lens that's exactly what you wanted or intended to come up with. But you do have to understand a little bit more about how Wave is applying all those changes to you. The idea behind the modification area is really to try and streamline that and make it a little less mysterious, so that you can come up with the changes and still end up hopefully right where you intend it to be.
Okay, that's great. And then we'll do one more question if that's okay with you.
Mm-hmm.
Okay.
Yep.
Any preference on recommending or upgrading from the legacy Wave software to the new Wave software that you showed?
Sure. The new software has really come a long way from its original release. And I believe that there's another release that's just about ready to happen that you can discuss with the Wave people, because I don't know exactly when that's coming out. I have been using that beta version. And certainly for the majority of applications, for most users, the new Wave software is phenomenal. There are many more changes that are actually coming to the new software that are not even available in the legacy software. And the reason I know that is because I keep feeding my desires into the software team as we need to get these things happening. So I'm very, very excited to see us moving into the new software and really leaving the legacy software behind, especially as some of these new powerful features are really being added in. I think that's going to be a wonderful platform.
Yeah, definitely. So I think that's going to wrap it up. Thank you so much. That was a lot of great information. Thank you for taking the time. And thank you to everyone who attended and submitted questions. And yeah, thanks for the great discussion. So this concludes our presentation. And on behalf of Wave, have a good night, everybody.
Thank you, Catherine, for running a good show tonight. And thank you for everyone that attended tonight and came out. I hope you do find this all very helpful to you in your Wave endeavors and getting your patients successful. And I look forward to seeing you next year at our next webinar.
Thank you, everyone. Good night.